So these are going to be some problems dealing with both sigma notation and then just general Riemann sums, intended for the tail end of a Calc 1 class from the beginning of a Calc 2 class. First question here, we want to evaluate the sum, summation k equals 1 to 3, k squared minus 4k. Now, I could just write these out. So one thing I could do here is just plug in k equals 1, k equals 2, k equals 3. So in k equals 1, I have 1 squared minus 4 times 1. And then plus when k equals 2 would be 2 squared minus 4 times 2. Plus when k equals 3, I'm going to get 3 squared minus 4 times 3. If you look at that, do that down here, I get 1 minus 4, that's negative 3. I have a 4 minus 8, that's plus negative 4, so minus 4. I have a 9 minus 12, that's a minus 3. Add those up, and I'll get a minus 10. So you could just do this one directly, adding up 3 things, not so bad. Now, another thing we could get used to, though, is using the formulas. So what we'll get is that this summation should be the sum k equals 1 to 3 of k squared. And then I can pull out a negative 4 here. Let's write it this way. How about? Well, let's just write it this way. Minus 4 times the sum k equals 1 to 3 of just k. So I can write this as a sum of k squareds and a sum of k's here. And the reason I'd want to do that is to make use of a couple of formulas. One of those formulas is that if I do a summation k equals 1 to n of just k, turns out that's n times n plus 1 over 2. And then if I add up k equals 1 to n k squared, it's kind of a similar formula. It's n times n plus 1 times 2n plus 1 all over 6 here. And if I add up, let's just do the other one we're going to use sometimes, which is k cubed. This one actually ends up being the k equals 1 to n of k formula squared. So it's n times n plus 1 over 2, that whole thing squared. One thing I'll point out here, if you're used to a little more calculus here, this one is kind of, if it was n plus 1 is basically n. That's more or less n squared over 2, which if you integrated, say, x, you'd get an integral of x squared over 2. This one, I have an n times a 2n. It's like 2n cubed over 6. That's going to end up being really like n cubed over 3, which would be the sort of, well, the antiderivative of x squared would be x cubed over 3, very similar. This one I'm going to get n times n is n squared. Squared, that's like n to the 4th. 2 squared is 4. That's like the antiderivative of x cubed, x to the 4th over 4. So there's some connections here. You don't need these particular relationships with these approximations. They just may help you memorize the formulas if you're forgetting exactly how it works out, is that they should fit some perhaps other known things. Okay, in any case, what I get now is k equals 1 to 3, k squared. It's going to be n times n plus 1 times 2n plus 1 over 6. So that's 3. 3 plus 1 is 4. 2 times 3 is 6 plus 1 is 7 over 6. Minus 4 times summation k equals 1 to 3 of k. So it's going to be a 3. N is 3. N plus 1 is 4 over 2. And now I could simplify these. Let's see, this 6 is going to be a 3 times 2. Cancel the 3's. 4 is 2 times 2. Cancel the 2's. So I get a 14, 2 times 7 from the first term. Here, let's say I could cancel that 4 with that 2. 4 times 12, 4 times 3 is 12, times 2 is 24, minus 24. I get the same negative 10 that way. So just two different methods to do the same question. Next one. Okay. Here we've got a negative 1 to the k plus 1 over k plus 3. What I'm going to tend to do with this is k equals 2 to 5. It's just 4 terms. I'm probably just going to write this out. So what I'm going to do is write out when k equals 2, I get negative 1 to the 3rd over 2 plus 3. That's 5. Plus when k is 3, I get negative 1 to the 4th over 3 plus 3. That's 6. plus when k is 4, I get negative 1 to the 4 plus 1 is 5, over 4 plus 3 is 7. Plus when k is 5, I get negative 1 to the 6th, over 5 plus 3 is 8. This all works out to be negative 1/5 plus 1/6 minus 1/7 plus 1/8. So not so bad, 4 terms added together. Could do some fraction arithmetic there. I'm going to just use my calculator instead. So we have a negative 1/5 plus 1/6 minus 1/7 plus 1/8 here. That spits out that ugly thing. If I go math to a fraction, should spit out this as negative, 43 over, it was 840. So there's my sum, and I just need to know sort of what this is. Now, you can also use your calculator sort of directly here. And what you do is you go to second list, go to math. You want to do a sum of second list, and then go to ops, pick out the sequence. And your sequence is going to be, say, negative 1 to the, instead of k plus 1, I'm going to use x plus 1, just because that's easier to type in, divided by x plus 3. And then you say comma, I'm going to add up x's, and I'm going to go from 2 to 5. So that'll close the sequence, close the sum. So the sequence just sort of writes out really the negative 1/5, comma the 1/6, comma the negative 1/7, comma the 1/8. The sum adds those up. I'm going to convert that answer to a fraction, and it spits out the negative 43 over 840. Now you could do that with all these, but the point is really to learn how to manipulate the sequences. It'll be more useful later on in the course when we deal with the series here. Okay. Next one, we're getting a bit bigger here. So k equals 1 to 18, 3k squared minus k cubed. Now I'm definitely not going to want to write this out because there's 18 terms. So what I'm going to get here is I'm going to rewrite this as 3 summation k equals 1 to 18 of k squared minus summation k equals 1 to 18 of k cubed. And then I'm going to use my summation formulas. So the k squared, so maybe just go copy those from up here. So let's just pull off these parts of it. Copy, and then we'll go down, go here, put those there, and let's put those formulas up there so we can look at them. And I lost my summation symbol in that copy on this one. There we go. Yep, everything else looks good. So summation k equals 1 to 18 of k squared. Keep my 3. K squared, I'm going to get n is 18, times 18 plus 1 is 19, times 2 times 18 is 36, times 1 is 37. I'm going to divide that by 6, and I'm going to subtract the formula for k cubed, which is 18 times 19 over 2, everything squared. And so what I'm going to get, let's maybe try and, well, let's just go ask our calculator now. There may be nice ways to do this, but I'm just going to ask my calculator. 3 times 18 times 19 times 37 divided by 6 minus 18 times 19 divided by 2 squared. It's going to spit out some answer is negative 22,914. Now, again, I'm just going to go use the sum sequence to check that. So I go to math, sum, ops, sequence. Some of the newer calculators have just a sigma type of thing. You could plug this in directly. 3x squared minus x cubed, comma x, comma, we're going from 1 to 18. Close a couple parentheses, hit enter, and I spit out the same answer there. Okay, next one. K equals 1 to 6, negative 1 to the k plus 1 k squared. I'm going to just write this out. It's 6 terms. I'm thinking that's not that bad here. So let's, and the negative 1 sometimes makes things more complicated. We'll deal with that in a bit, though, with the still may be greater than 6 in the next question. So in k equals 1, I get negative 1 to the k plus 1, that's 2, times 1 squared, plus negative 1 when k is 2, I'm going to get to the third, times 2 squared, plus negative 1 when k equals 3, I'm going to get to the fourth, times 3 squared. When k is 5, I'm going to get negative 1, sorry, no, when k is 4, I'm going to get negative 1 to the fifth, times 4 squared. When k is 5, I'll get negative 1 to the sixth, times 5 squared. And when k is 6, I get negative 1 to the seventh, times 6 squared. Okay, note here, negative 1 squared is 1 times 1 is 1. Negative 1 cubed is negative 1 times 4 gives me a minus 4. Next one, I get a negative 1 to an even exponent, that's going to be a positive 1. 3 squared is 9. Negative 1 to an odd, that's going to be a minus 1. 4 squared is 16. Negative 1 to an even is plus 1. 5 squared is 25. Negative 1 to the odd power gives me a negative 1. 6 squared is 36. Note, there's sort of a common structure here. When you have this negative 1 to the k plus 1, I get a plus, minus, plus, minus, plus, minus. This is actually called, the term we'll see later on, particularly to a series, which is like a summation to infinity. But this is called alternating. It goes between positive and negative. Sort of a nice sort of example of that pattern there. Now we could add these up. Let's see, negative 1 minus, or sorry, 1 minus 4 is negative 3. 9 minus 16 is minus 7. 25 minus 36 is minus 11. Let's see, 7, 3 is 10. 11 is 21. So these all add up apparently to negative 21. So that one I can do straightforward here. Next one, you'll see is actually the exact same sum, but instead of 60, or sorry, instead of 6, I'm going to 60. So I could write this out, but then I'd have to do 60 different terms. I don't really want to do that. So I'm going to have to try something a little more creative here. There's a couple things you can do with this. Let's see. So one thing you could do, let's see, is you could split this up. Let's write it this way. So let's maybe think of this as, okay, so how about negative 1 squared times 1 squared. Now, I'm not going to write the negative 1. Well, let's leave the negative 1 squared. Well, let's just not write it. So that's plus 1. So I plug in k equals 1, that's plus. I'm going to get 1 squared, and then I get minus 2 squared, and then I get a plus 3 squared. Somehow I feel like that's, yep, that's fine. Minus 4 squared, plus 5 squared, minus 6 squared, so forth and so on. The last couple terms, I'll get a plus 59 squared and a minus 60 squared. So you could write this out like that. The dot, 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 sort of indicating the summation here. I really haven't done a lot to help myself yet. But what I'm going to do is regroup this. So what I'm going to do is sort of group those two, group those two, group those two, group those two. And so what I get is I'm going to get a summation. I'm going to call it A just for lack of a better letter. I'm going to start at 1, so this is like A equals 1 here. Let's maybe write that in red. So this term here, that's A equals 1. I want this pair to be A equals 2, this pair to be A equals 3. Last pair, if you think about it, there were 60 terms to start with. I sort of split them into pairs, and so there should be half as many. This is like A equals 30. So I'm going to get a summation A equals 1 to 30. And then I want to sort of think about what this pair is. So the first bit, when A equals 1, that's sort of the odd one. Second one is actually 2A. So the 4 is 2 times 2, the 6 is 2 times 3, the 60 is 2 times 30. So this first one is 2A, but minus 1 squared, not plus, minus 2A squared. So this 2A minus 1 squared minus 2A squared gives me one of the sort of groupings of parentheses in red, so there's 30 total. And now I'm just going to do some algebra. 2A minus 1 squared is 4A squared, minus 4A plus 1. 2A quantity squared is minus 4A squared. Well, then the 4A squareds cancel. plus and minus. And so I'm left with negative 4 times the summation a equals 1 to 30 of just a plus summation a equals 1 to 30 of just 1. Okay, so what we get is negative 4, summation a equals 1 to 30 of a. The formula was n, thing we sum up to, 30, times n plus 1 over 2. So that gives us that summation. Now this other one, I didn't write down a formula to sum up 1 from 1 to 30, but let's think about what's going on here. Is this summation, let's maybe write that in. How about green off to the side? How about red? Do it in red. Summation a equals 1 to 30 of 1. This is 1 plus 1 plus 1 plus 1 plus 1, and there's 30 of these 1s. That's just 30 here. So it's like 1 plus 1 plus 1 times itself 30 times. So that's just a 30. And so what I'm left with then, let's see, this 4 and 2 will cancel with a 2. So this is minus 60 times 31 here. So I'll get a minus 60 times 31. So that's going to give me a negative 1860 plus 30. In the end, I end up with a negative 1830. So there's sort of my answer there. So that works out. There's another way, kind of running out of space here, but there's another way I can group this as well. And that is I can do the k equals 1 to 60, negative 1 to the k plus 1, k squared. Sort of another thing you'll sometimes see here is I'm going to rewrite this as, well, let's write it this way. So this is our 1 squared minus 2 squared plus 3 squared minus 4 squared plus 5 squared minus 6 squared plus 59 squared minus 60 squared. I'm going to rewrite this as 1 squared plus 2 squared plus 3 squared plus 4 squared plus 60 squared. So I've got that, but then I have to subtract off. Well, I got a plus 2 squared. I need a minus 2 squared. So I have to subtract off 2 of those 2 squareds plus 4 squareds plus 6 squareds, the even terms, all the way up to 60 squared. Now, why would I want to do that? Well, this first one, this is a summation of squares up to 60. So that's 60 times 61, n times n plus 1 times 2n plus 1. It's 121 over 6. This second one I can write as negative 2. I'm going to pull out a 2 from each of the things squared. That'll be a 4 on the outside. That'll give me a 1 squared plus 2 squared plus 3 squared plus blah, blah, blah. And then once I divide 60 by 2, that'll be a 30 squared. And so what I'm left with, 60 divided by 6 gives me 10 times 61 times 121. Minus 2 times 4 is 8. And then this, sum of squares, but only up to 30, is going to be 30 times 31 times 61 over 6. And then you can add that up, maybe on a calculator. 10 times 61. Okay, that's 610 times 121 minus 8 times 30 times 31 times 61 divided by 6. And that spits out not what we want here. Let's see, what went wrong here? 10, oh, it shouldn't be 12, it should be 121. So maybe nothing went wrong other than I typed things into the calculator wrong. There's our negative 1830. Okay, so that spits out a negative 1830. Get the answer that way as well. So two different methods have a little bit different feel to them. Both are a little bit more sort of creative when you've got those negatives. They're both nice things to be able to use later on when we manipulate series more towards the end of Calc 2. Next one. Okay, so now we're going to estimate the area under the graph of y equals x squared plus 4x from x equals 2 to 6 using a Riemann sum. And we're going to use left endpoints in 20 intervals. So general idea here, x squared plus 4x. I don't necessarily really care what that graph looks like. Let's just draw it like, let's draw it a little more curvy. Well, failed at that. So let's go here. Whoops. A little straighter up there. So you have 2 to 6. And then what I'm going to try and do is split this into a bunch of rectangles. Here'd be 1, 2. If I'm using left endpoints, there's 3. And then that last one may be like that. Here, I'm going to split that into 20 rectangles, add up the area of those 20 rectangles, and that should approximate the area under the curve here. So I could do that directly. It's 20 things to add up. That gets a little bit annoying. I'm going to do something using the summation instead. So what I'm going to get here, I'm going to think of 2 as A. So that 2, I'm going to think of that as A. The 6 is B. The 20 is my N. So a couple things here is the width of one of these rectangles. I'm going to call that delta X. It's sort of this width of one of these red rectangles here. So this little area here. So what I'm going to do is I'm going to take, it's really B minus A over N. So the right endpoint minus the left endpoint, that gives me the whole distance here of 4. So it's 6 minus 2, that's 4. And then I have 20 rectangles, so I divide by 20. Each of those rectangles will have width of 1/5. So that should be fairly intuitive. So width of a rectangle. And then the height is really going to be, well, just f, so that's x squared plus 4x. So f of x, where x is the left endpoint. So to do that, I need to do left endpoints. I need to write those really using a k. So what I'm going to get is I'm going to start with 2 plus, well, the first one's 2. And what I'm going to choose to do is write it as k times really delta x here. And that's going to be 1/5. So that's times a delta x. The idea being I'm at 2 on the left here, increased the next one, and I sort of just added the width of that rectangle. Go to the next one, added the width of the rectangle. Keep adding the width of the rectangle to get sort of the left endpoints. And that's 4. Now I got to be careful. K equals, the first one on the left is going to be k equals 0. Up to k equals the last one. I'm not going to get all the way to 20. That'd give me 4, and that'd be 6. I'm only going up to 19. So 0 to 19 is actually 20 different numbers here. As an alternative, you could write these as 2 plus k minus 1 times 1/5. And then you would do k equals 1 up to k equals 20. Either of those work just fine. They're essentially the same thing. Here, I sort of have a choice there. Let's put both of them there because you may see both in different scenarios. Well, then the height, now just not just of any rectangle, but of the, let me write that cleaner, the kth rectangle. So what that's going to be now is it's just going to plug in, I'm going to use this in blue, the 2 plus really k over 5 into this formula. So it's 2 plus k over 5 squared plus 4 times 2 plus k over 5. So let x be the 2 plus k times 1/5. That's the same thing as 2 plus k over 5. Just plug that in for x here. And so that's really just taking my left endpoint and evaluating the function there. Okay, and so my area, let's just go here. So my area under the curve, what I'm going to get for my area, I'm going to add up the areas of all these rectangles. So I'm going to do a summation, k equals, I use the blue point, so this is going to be 0 to 19. And I'm going to get the height of the rectangle. That's 2 plus k over 5 squared plus 4 times 2 plus k over 5. So that's the height times the width of the rectangle. That's 1/5. Then I'm just going to simplify this down. So goal 1 is write this down somehow and then use sort of our sequence summation manipulations to make this work out. So first thing I'm going to do is pull that 1/5 out of the summation. K equals 0 to 19. Let's see, I'm going to get a, 2 plus k over 5 squared. That's going to be a 4 plus 4k over 5, first times second times 2, plus k squared over 25. Next part is going to be 4 times 2 is 8, plus 4k over 5. And if you put that together, what we get is 1/5 times, okay, we've got the 4 plus 8. So let's just look at it this way. Summation k equals 0 to 19. 4 plus 8, that's a 12. The k terms, we have a 4/5 and a 4/5. So that's 8/5. Summation k equals 0 to 19 of k. And then the k squared, we just have the 1. It's a 1/25. So we get 1/25. Summation k equals 0 to 19 k squared. Here. Okay, so now we're going to use our formulas here. I'm going to get 1/5. Now, summation k equals 19 of k equals 0 to 19 of 12. This is 12 plus itself really 20 times. There's 20 different terms there. There's no k's here, so that's 12 times 20. It's going to work out to be 240. Next one is 8/5. Now, something to note here, summation k equals, let's just write this off to the side, k equals 0 to 19 of k. The formulas we had started at k equals 1. We've got this k equals 0, but it turns out we can just drop that term, because when you plug in k equals 0, that's just 0. So this is like 0 plus 1 plus 2 plus some stuff up to 19. Well, I can just get rid of that 0, because adding 0 to a sum doesn't do anything. And so this is just exactly the same thing as k equals 1 to 19 of k. So I can use my formula starting at 1 or 0 if I have the k or the k squared. That didn't work here because I didn't have the k equals 0 to make that first term 0. It's still 12 even though k is 0. In any case, what I'm going to get is n, it's 19, times n plus 1 is 20 over 2, plus 1/25. This one, the k squared formula is I take n times n plus 1, and then times 2n plus 1. 2n is 38, plus 1 is 39, and then divide by 6. And there I've got, now this would be a closed form here. There's no more summations. We can just plug this directly into basically any old calculator. We get a 1/5. That was maybe a little bit, whoops, missing here on the left. And then we're going to multiply that by 12 times 20 is 240, plus 8 divided by 5 times 19 times 20 divided by 2 is 10, plus 1 divided by 25 times 19 times 20 times 39 divided by 6. Close, whoops, I didn't get my 6. Close parenthesis, and this works out to be something like 128.56. And if I wanted to write that as a fraction, might make sense here. Exact answer, 3214 over 25. So apparently that is our summation. Now you could again go and check that, all this sort of math here, with this original sort of formula here, with using the sum sequence. So go to second list math sum, second list sequence. I'm just going to sort of do this directly. So 2 plus, I'm going to use x for k, squared, plus 4 times 2 plus x over 5, comma x, and I'm going from 0 to 19. Close the sum, close the sequence, and then I have a times 1/5. That's like divided by 5. And then let's go to a fraction, and hopefully works out to be the exact same thing. There. So we could have done that directly. I think there's some value, though, to going through and learning how to work with the summations. That will come into play and make you a little bit sort of stronger when we get to series. Next one. Okay. Write endpoints and 20 intervals. So this is the exact same thing as from before, except we're going to use right endpoints instead of left endpoints. So what that means is that in this picture, I'll try and do it with green, is this first rectangle is going to have height really there. Second rectangle is going to have height there. Third one is going to have height there. And this last rectangle is going to have height there. So if this is an increasing function here, which it will be on this particular interval, this is going to give us an overestimate, whereas the previous one gave us an underestimate. Really, what's going to change here is that our left endpoints are going to change to right endpoints. All that's really going to change is we're going to get the 2 plus k times 1/5, or 2 plus k over 5. But now we're going to go on the right endpoint is going to go from, well, we want to start with 2 plus 1/5. So the first one we actually want to be k equals 1, and that last one to be 20. So you can just shift those over here. There's an alternative formula you could use here as well, but I think this sort of makes more sense. 2 plus k over 5 for k equals 1 to 20. And essentially all that's going to do here is it's going to change this from 1 to 20, this from 1 to 20, this from 1 to 20. Really, it's just going to change this 19 to a 20, 20 to 21. I'll get a 20, n plus 1 is 21, 2n plus 1 works out to be 41. Just get some small changes here. Note everything got bigger, should give us a bigger number. And I'm going to maybe not write that all out again. Could go through it as practice. But you get 12, whoops, I think there was a 1/5 on the outside. 1 divided by 5 times 12 times 20, that's our 240, plus 8 divided by 5 times 20 times 21 divided by 2, plus 1 divided by 25 times 20 times 21 times 41 divided by 6. And then I'm just going to convert that to a fraction, and that's 3454 over 25. So this works out to be 3454 over 25, using the exact same thing we just did. We're just shifting over one. And you could even use the sum sequence, hit second enter a couple times to bring up what we did here. And essentially, instead of going from 0 to 19, you go from 1 to 20. And it gives you that 3454 over 25. So things got a little bit bigger. The true value is going to be somewhere in between these here. Okay, now what I could do now is use 40 intervals. So you could play this game again, use 40 intervals, go through everything, but all the algebra is going to work out pretty much the same. I'm just going to replace effectively 20 with 40. So what I'm going to do, just go up and maybe copy what we've got here. So really we're just making the n be 40. And so I'm going to get, let me just copy the formula here. Let's just do this whole bit here. Actually, let's copy everything we've got here. So let's copy this. Move it down here. Paste. Oh, that went there. We'll just leave that there. How about that? Whoops. And then let's get our pen back. Okay. Let me do this whole thing in green here. So what we're going to get, width of rectangle. Now that's actually going to change here. So our delta x, that's our width of our rectangles. It's b minus a, that's still 4. But if you notice, we divided by the number of rectangles we had. So that was 20 before. Now we're going to use 40 here. So that gives us 1/10 here. Left endpoints. So our left endpoints. Now, just notationally here, these are going to be written sort of a lot of times as maybe an xi. Or actually, I'm using k, so let's do this as x sub k. And what this is going to be is it's going to be that 2 plus essentially k times delta x, which in our case is 2 plus k times 1/10. Same thing as 2 plus k over 10. And that's 4 we got to think about. On the left, we want the first one to be when k equals 0. We don't really want that plus delta x. So this is going to be from k equals 0 up to k equals the last one. Well, we want 40 in total. 0 to 39 would give us 40. So actually don't want to go to 40 of these. That'd put us at the right endpoint, which of the whole sort of interval, which we don't want. There's our left endpoints. So then the height of a rectangle, maybe the kth rectangle, that's f of xk, and that's going to be, let's see, it was, I forget what the function was, but apparently it was x squared plus 4x. So this is going to be 2 plus k over 10 squared plus 4 times 2 plus k over 10 here. And so our area, the general formula is I'm going to sum up when I'm doing left endpoints, and I'm using this sort of 0 to 39 setup here. So this general formula is k equals 0 to n minus 1. It's f of xk times delta x, and sort of really our formula for xk, if you want a general formula, is going to be, let's see, it's going to be a, the left endpoint, plus k times delta x. And delta x was b minus a, right, minus left endpoint over n. So there's our general formulas here. But in our case, this is just the height of the rectangle times the width of the rectangle. So summation k equals 0. N is 40, so I get summation k equals 0 to 39. F of xk, I'm going to square this out. So it's 2 squared is 4, plus 2 times k over 10 times 2. Let's see, it's going to be plus 2k over 5, or 4k over 10, plus k squared over 100, plus 4 times 2 is 8, plus 2k over 5. So it's just the f of xk, and then our delta x was really 1/10. And now we need to work that out. And so what we get, I'm going to pull the 1/10 out. We get a summation k equals 0 to 39. You get 8 plus 4, that's 12. I'm going to do this a little bit differently than last time. I'm going to factor the 12 out and say it's a summation of 1. Put the 12 inside last time. They're roughly equivalent. They are equivalent, just a little bit different way of thinking about things. The k's, I have a 2/5 plus a 2/5. That's a 4/5. K equals 0 to 39. K, again, I could start this at 1 because when I plug in k equals 0, I get 0 anyway, which doesn't affect the sum. Plus, I have a 1/100th. Summation k equals 0 to 39, k squared. There's my k squareds, there's my k's. So I end up with 1/10 times, let's see, 12, and there's 40 terms. So I get 12 times 40 plus 4/5 times the 39 times 39 plus 1 is 40 over 2 plus 1 over 100 times, let's see, the squareds is n times n plus 1 plus 2n, or so not plus, times 2n plus 1. 2n is 78, so I multiply by 79, all over 6. And that works out to be 1/10 times, in parentheses, 12 times 40 is 480, plus 4 divided by 5 times 39 times 40 divided by 2, plus 1 divided by 100 times 39 times 40 times 79 divided by 6. And I'm just going to convert that to a fraction. I get 6547 all over 50. So I get 6547 over 50. Now, let me just, let's just do that. 6547, whoops, over 50. Let's get that as a decimal, 130.94. Note, this previous left estimate was 3214 over 25. So we're expecting these to be lower bounds, it turns out, in this case. So I should get 130.94, should be a little bit higher. You can see this went up from 128.56 to 130.94. Still too big. Note the upper estimate we had before was 3454 over 25. So this should be too big. Should be so really 138.16. So we're somewhere between 130.94 and 138.16 for the true area here beneath this curve. And now this was left endpoints with 40 intervals. You can do right endpoints and 40 intervals. Now again, that's going to be the same thing that we did up here, except for right endpoints. Here, what's really going to happen is I'm just going to go k equals 1 to 40. There's other ways to write this down. I think this way is a little bit simpler. And that just changes our summation bounds from 1 to 40. And if we chase that through, really all that's going to happen is I'll get a 1 to 40. That doesn't really change things. Get a 1 to 40 here, and a 1 to 40 here. Now, this first one, 12 times 40, doesn't matter. But here, that 39 becomes 40. 40 becomes 41. 39 is 40. N plus 1 is 41. 2n plus 1. 2n is 80 plus 1. That's 81. So we had a slightly different formula here. And I'm just going to hit second enter a bunch of times to bring in what I typed in and change the appropriate thing so that 39 becomes a 40. The 40 becomes a 41. The 39 again will become a 40. The next 40 becomes a 41. And the 79 becomes an 81. And you would enter, and you get 6787 over 50. So this is 6787 over 50 here. And so what you should get, here's something that should be, let's see, it was 138.16 was an upper bound. This should be a little bit smaller. 6787 divided by 50, but bigger than the previous estimate, but 135.74. So we get a sort of better upper bound. And you could keep repeating this instead of 40, do 60, do 80, do 1,000 here. You might tire of this, and eventually you're going to want to do this with n intervals. So this is sort of the general form here. So you do this, and if we do n intervals, what I'm going to get is my delta x. That should be b minus a. That was 6 minus 2. Turns out, right, we were 2 to 6. Got to remember that from way up here. 2 to 6, yep. It's x squared plus 4x. So it's x minus 2 over, I don't know how many intervals. I'll put an n here. So that's 4 over n. Let's see, my x sub k, that's really my left endpoint. It's going to start at 2 plus k times delta x. So that's 2 plus really 4k over n, and that's going to be for k equals 0 up to k equals n minus 1. So I have to have n total rectangles. And then my f of xk, so it was x squared plus 4x, so that's 2 plus 4k over n squared, plus 4 times 2 plus 4k over n. So there's my f of xk. And so my area estimate, if I use n intervals and left endpoints, should really be the summation k equals 0 to n minus 1. I'm going to take f of xk, so it's going to be 4 plus 2 times 4 is 8 plus 16k over n plus 16k squared over n squared. I'm going to distribute the 4 here. 4 times 2 is 8. 4 times 4k over n is 16k over n. So this is f of xk. That's the height of the kth rectangle times the width of the kth rectangle, which is 4 over n. So I get this area formula. Now my goal is to get a formula in terms of n that don't have any more of the k's. So I can do the same thing we've been doing. So I'm going to write this as pull out the 4 over n. Note the n can go outside of the summation because this is a summation with respect to k. It's an n on top, but k is my indexing variable. And I'm going to get a summation k equals 0 to n minus 1. 4 plus 8, that's 12. Maybe I'll write this not as a parenthesis, but a big square bracket. Now with the k's, I'm going to do summation k equals 0 to n minus 1. With the k's here, I can pull out, let's see, 16 over n plus 16 over n is 32 over n. I can write that outside and just leave the k here. So the k has to stay inside of the summation because sort of the value changes depending on what k is. 32 over n, that value does not change with k. So I get another formula, or another term. And then the k squareds, I can pull the 16 over n squared out. But then I need my k squared term. So I get my formula. This should feel very much like what we've been doing, just with n's instead of a 20 or a 40 or maybe a 19 or a 39. So this spits out as 4 over n, 12. There's n terms here, so it'll be 12n plus 32 over n. Summation k equals 0 to n minus 1 is n minus 1 times n minus 1 plus 1, which is n, over 2. And then we get a 16 over n squared. And we get, let's see, the formula when we sum up k squareds is the top bound, the n minus 1, times n minus 1 plus 1, that's n, times 2 times n minus 1 plus 1. It's actually going to be a 2n minus 1 when we're done, all over 6. And then we can clean this up a little bit. So we'll have a 4 over n times 12n. See, these n's cancel. I'm going to get, let's see, 32 over 2. That leaves me with a 16. So that's plus 16n minus 16. Here, so I can cancel a 2 out of the 6 as a 3, leave the 16 as an 8 here. This n squared, I can cancel one of the factors of n with the n there. And so I'm going to get a plus 8 over 3n. Then on top I have n minus 1. Again, this was 2n minus 1. 2n minus 2 plus 1 gives me 2n minus 1. So I get 2n minus 1 times n minus 1. That's 2n squared. So minus 2n minus n minus 3n plus 1. Here. All of this is 4 over n. 12n plus 16n is 28n. Minus 16. Let's see, we have plus 8 thirds. 2n squared over n is 2n. Let's see. Minus 3n. Let's just do it that way. So 8 times 2n squared is 16n squared over 3n is going to be, let's see, 16 thirds n. 8 over 3n times negative 3n, I'm going to go on, is going to be a negative 8. 8 over 3n times 1 is going to be plus 8 over 3n. And when I combine these all together, so I have 4 over n, 28n plus 16 thirds n. See, 28 is 60, 84n plus that would be 100 thirds, or 100n over 3. Minus 16 minus 8 is minus 24. And then we have a plus 8 over 3n. And then I can distribute the 4 over n. Gives me 400 over 3. Minus 24 times 4 is 96 over n. 4 times 8 is plus, let's see, 32 over 3n squared. So that is really our formula here. So this took a lot of work here. This is one reason why we'll like sort of the fundamental theorem of calculus and be able to use antiderivatives to do this. So this gave me a formula for n integrals, or sorry, n rectangles. Now the idea here is that I could take a limit of this as n goes to infinity. So what I'm going to do is, this is really answer the question as it's asked. But the general idea is you have this and sort of say, well, what would happen if I had an infinite number of rectangles? limit as n goes to infinity, 400 over 3 minus 96 over n plus 32 over 3n squared. Well, these last two terms are just going to go to 0, so that gives me 400 over 3. So that tells me really the area of that under the curve should be 400 thirds. So if we go back to our calculations, we can check a couple things. 400 over 3, that's 133.33. That's sort of in between really the upper bound we had, and the lower bound was like 132 point something. Another calculation we could do, just go up with the 20, I forget what the number was, 3214 over 25. So that was 20 intervals and, oh, that was right endpoints, sorry. Oh, sorry, we copied that for the next one here. So this is actually, I've got the wrong answer here. It's the 3454 over 25, but it's 3214 over 25 for the left intervals. So what we could do is, the idea is if you plug in a 20, just type it in, 3214 divided by 25, that was my left intervals. If you plug in an n equals 20 to this formula here, you should get that 3214 over 25, or 128.56. So 400 divided by 3 minus 96 divided by 20 plus 32 divided by, in parentheses, 3 times 20 squared. And that spits out the same thing. So it sort of checks the answer earlier. Now you could do this again with the 40 instead. So one of the other previous questions, you get the 130.94, which hopefully matches the 6547 over 50. There, that matches. So note here, if you were actually trying to do all these questions, say in an exam or a homework, despite the fact that it's harder, I would do part E first, because you have to do that anyway, and just use this result with n equals 20 and n equals 40 plugged in to get part A and C. Be a little more efficient than working everything out separately. A bad thing to see what's going on. Last one here, we're going to do right endpoints and n intervals. It's just like this previous question. So left endpoints, right endpoints. What changes is their summation goes k equals 1 to n here. So that's our right endpoints. That's one way to write that down here. So really we get a sum k equals 1 to n, 1 to n, 1 to n, 1 to n, and that's going to change things up here. So I'm going to go and just sort of copy this bit, see if we can get exactly what we want here. Close. Copy, and then I'll just write down that formula there. Or just copy that and drag it down here. Back to my blue pen here. Straight mark there. So this is the formula we want. So this is 4 over n. Let's see, 12, this is still n, so it's still 12n. Then we get plus 32 over n. Now the formula k equals 1 to n of k. That's going to be n times n plus 1 over 2. From 16, or then times 16 over n squared. K equals 1 to n of k squared. That's n times n plus 1 times 2n plus 1 over 6. So you get a slightly different formula. So then we want to simplify this down. 4 over n, get 12n, cancel the n's. 32 and 2 give me a 16. So it's plus 16 n plus 16 if I distribute the 16. Here this n cancels with the square. 6 becomes a 3, 16 becomes an 8. So we get 8 over 3n times n plus 1 times 2n plus 1. 2n times n is 2n squared. 2n plus 1 is 2n. 1 plus n is plus 3n. 1 plus 1 is 1. So I get, let's see, 4 over n. 12n plus 16n is 28n plus 16. Distribute this out. You'll get 16 n over 3. N squared over n gives me n. Plus 3n's cancel, get a plus 8. Plus 8 over 3n. And then this will be, let's see, 4 over n, 28n plus 16n over 3. 28 times 3 is 84. So this is 84 thirds. So I get 100n over 3. 16 plus 8 is 24. Plus 8 over 3n. Then distribute the 4 over n. I get 400 over 3, sort of the constant part that we want. The rest should go to 0 as n goes to infinity. 4 times 24 is 96 over n. And then we get plus 32 over 3 times n squared. So there's our formula if we wanted to do the right endpoints. Let's just look at these two. I'm going to copy this one here so we get a sense here of what's going on. Get both of them side by side. Doing left endpoints and right endpoints. Well, that didn't really help. Let's copy this again. Oh, it doesn't really want to do that. Well, it's 400 over 3 minus 96 over n plus 32 over 3n squared. Really, all that changed here is this plus here is either plus or minus. So that 96n over n really gives you sort of the difference between doing lower sums and upper sums. You can now then quantify how much of a difference there is here. But as n goes to infinity, you get really the same thing. That difference goes to 0, so it doesn't really matter which way you are. Okay, so that ends this worksheet working with Riemann sums and sigma notation.